All right. Well, happy Valentine's Day, everybody. Happy Friday. I hope you have a great day today, whatever you have planned. uh, we get to continue on in this exciting topic of floating point numbers. So on Monday, we introduced the IEEE 754 specification for floating point numbers, where we said, in the computer, all of our numbers are stored in binary, and we have double precision floating point, which means we will use 64 bits to represent numbers. Okay, and with 64 bits, we allocate 1 bit for the sign, 11 bits for the exponent, 52 bits for the mantissa. So this is how we allocate our bits, and that's for double precision floating point. Now, to kind of learn about the floating point system, we are going to explore this using a miniature version of the floating point system. In this system, we will have only 8 bits, so we have not very many numbers we can represent. Just only 8 bits, and we're going to allocate them with 1 bit for the sign, 3 bits for the exponent, and 4 bits for the mantissa. Okay, and so when we have 3 bits for the exponent, that means I can represent a total of 8 unique values. Oh, sorry, the sign bit, 0 if it's positive, 1 if it's negative. Okay, with 3 bits for the exponent, I can represent 8 unique values. All zeros to all ones, 8 unique values. We set aside all zeros for a special case. We set aside all ones for a special case. The remaining 6 values we use to represent the exponents. We're going to have half of those be positive. So we'll have 3 positive values. One of them will be 0, and the rest will be negative. So we have a bias of 3. Okay, so whatever my exponent is, I'm going to subtract 3 off of it. Okay, and that's going to be basically 2 to that power is going to be my exponent. And then the remaining 4 bits are in the mantissa, and those go into this section 1 point something 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 something. The 4 bits fill in here, and remember, after the binary point here, this is the 1/2 place. A space to the right is the quarters, 2 to the negative 2. A space over to that is 2 to the negative 3, 1/8. And then a space over to that is 2 to the negative 4, or 1/16. Okay, 1/16. So here is an exercise. I want you guys to try this out, and like for real, with a little bit of pencil here, and then see if you could figure out what number does this represent. And then once you get something, compare with your neighbor. All right. So we have 1 for the sign, 0, 1, 0 for the exponent, 1, 0, 1, 0 for the mantissa. 1 bit for the sign, 3 bits for the exponent, 4 bits for the mantissa. So I'm going to pause the video. I want you guys to try this out for a couple minutes, see if you get a number. Okay, well let's talk through this. All right, do we have a positive number or a negative number? We have a negative number, right? Our sign bit is 1, so that's a negative number. Okay, what is our exponent? We have 0, 1, 0 in the exponent, so that translates to what? A value of 2, and when we apply the bias of 3, our exponent becomes 2 to the negative 1. Okay, so whatever it is, it's going to be mantissa times 2 to the negative 1, or times 1/2. My mantissa bits are 1, 0, 1, 0. So my leading digit is what? A 1, 0.1010. So I've got 1 plus 0.1, so 1/2. No quarters, plus 1/8. Okay, so I've got 1 plus 1/2 plus 1/8. What is that? 1 5/8. Okay, so my mantissa is going to be 1 5/8 times 2 to the negative 1 times 1/2. So 1 5/8 times 1/2 is going to be, so 1 5/8 is 13/8. 13/8 times 1/2 is 13/16, and it's a negative, so we're going to get negative 13/16. Okay, so I've got my exponent is negative 1, my mantissa bits will be 1.1010, so that's 1 plus 1/2 plus 1/8, so that's 13/8 times 1/2, so 13/16 negative. All right, is that okay? Another way we can do it is you could roll over the binary point to 0.11010, and that will be 1/2 plus 1/4 plus 1/16. That will also give you 13/16, and then it's negative, so you get negative 13/16 as well. Okay, one issue that we have with our floating point system as it is we don't have a way to represent 0. Because if I have all zeros here, if my thing is all zeros, we feel like this should be 0, but what do we end up getting? All right, my exponent bits are all 0, and if my bias is -3, this is 2 to the -3, and I've got a leading mantissa of 1. Okay, I've got 1.0000, and that would be equal to 1/8. Okay, that would be equal to 1/8. Yeah, 1 times 2 to the -3, this would give me 1/8, and we don't have a way to represent 0. So this is why we have the special case. All right, when we say if the exponent bits are all zeros, that's a special case, and in the floating point system we call this denormalized mode, denormalized or subnormal. Okay, denormalized or subnormal mode. And you know, it's useful for us to assume the leading digit, the bit in front of the binary point, is always going to be a 1. Okay, because everywhere else that's going to be the case, and so you know it would be redundant, or it'd be a waste to kind of store that information. Okay, but there are some times where we legitimately want to have a 0 as the leading bit. Okay, and so we have subnormalized or denormalized mode, and in that case the digit in front of the mantissa bits is going to be 0, right? And to kind of prevent a jump in the numbers, the exponent bias is 1 less than usual. Okay, so our exponent bias is going to be just 2. Okay, it's going to be 2 in denormalized mode, right? So double precision exponent bias will be 1022. When we're doing our mini floating point system, instead of 3, it's going to be a bias of just 2. All right, so what we will have is, if we put in all zeros here, my exponent is going to be 0 with a bias of 2, so my exponent is going to be 2 to the -2. So now I have 0.0000 times 2 to the -2, and that's going to be 0. Okay, we're going to have all zeros in the mantissa bits, and my leading digit is 0 in denormalized mode. The other special case is when we have all 1s in the exponent. If we have all 1s in the exponent and all zeros in the mantissa, that's going to be infinity. Okay, that's going to be infinity. And then if we have all 1s in the exponent and not all zeros in the mantissa, we have some other thing, that's going to be nan. That's going to be not a number, nan. Okay, this is the smallest positive value we can represent in our floating point system. Okay, basically all zeros in the exponent, my mantissa bits are all zeros with just 1 1 at the end. Okay, this is the smallest possible number I can represent that's not 0. I guess, yeah, smallest positive number I can represent. So what is this? My exponent bits are 0 0 0. That means I'm in denormalized mode, so my bias is only going to be 2 rather than 3. So my exponent is going to be 2 to the -2. My mantissa bits are 0 0 0 1. So what is that? That's going to be, so this is the halves spot, quarters, 8 spot, this is going to be 1/16. So I'm going to have 1/16 times 2 to the -2. 2 to the -2 is 1/4. So 1/16 times 1/4 gives me 1/64. This is the smallest possible number I can represent, 1/64. Okay. What is the next smallest value? Okay. The next value is, I'm basically just going to count up in binary. So I start off with 1. The next number in binary is 2. Okay. That's going to be 1 0. So we're we're going to have, my bits will become 1, 0. And this will be what? So my exponent is still 2 to the negative 2, because I've got all zeros. I'm in denormalized mode. So I've got the exponent is negative 2. My mantissa bits are 0, 0, 1, 0. And in denormalized mode, the leading digit is 0. So we're going to have 0.0010. So that's 1/8 times 2 to the negative 2. That's going to be 1/32 or 2/64. Okay, so my smallest number is 1/64. My next number is 2/64. Okay, all right. What is our next number? So we're going to count up from 2, and we count up to 3, and the next number would be 3/64. And counting up in binary, we end up at 4/64, and then we get to 5/64, and then 6/64. And we keep going, and then the largest number we get in denormalized mode, we will have 1, 1, 1, 1 for the mantissa. I'm still in denormalized mode because my exponent bits are still all 0. So my exponent is still 2 to the negative 2. My mantissa bits are 0.1111, so that's going to be 15, all right? 1/2, 1/4, 1/8, 1/16. That's 15/16 times 2 to the negative 2, so that's going to be 15/64. Okay, so we've basically been counting up by 64ths. We started off here at 1/64, okay, and then this goes up to 2/64, then 3/64, 4/64, 5/64. We're at 15/64. Okay, what is the next number going to be? All right, so the next number, I'm going to, like, if I add 1 to this, so it's kind of like the odometer on your car. When it's like 999 and you add a 1, it becomes a 1, and then it becomes all zeros, right? It rolls over. And that's basically what's going to happen here. I add a 1 here, and this rolls up to a 1, and then the rest becomes 0. Okay? Now this means my exponent bits are 0, 0, 1. I'm now in normalized mode. In normalized mode, my exponent bias is 3. So my exponent is 1 minus 3. My exponent is still negative 2. Okay, so in denormalized mode, my exponent was 2 to the negative 2. I had 0 with a bias of 2. Here I have 1 with a bias of 3, so I'm still at 2 to the negative 2 for my exponent. Okay, my mantissa bits are all zeros. So what is this equal to? This is going to be 1.0000, so that's just 1, times 2 to the negative 2. That's 1/4. Okay, but if you think about what is 1/4, that's 16/64. So we went from 15/64 to 16/64. Okay, or 1/4. 1/4 is 16/64. Okay, so what's the next number going to be? I'm going to change this bit to a 1, and what is that going to be equal to? Okay, yeah, if I add 1 here, this will become 17/64. Okay, so here our exponent bits are all 1. My exponent is 2 to the negative 2. Mantissa bits 0, 0, 0, 1. Okay, so this is 1 and this is 1/16. I have 1 plus 1/16 times 2 to the negative 2. So this is 17/16 times 1/4. So this will give me 17/64. And then if I add 1, I keep counting. That will give me 18/64, 19/64, 20/64, 21/64, 22/64. I'm in normalized mode. And we can keep going. The largest value I have where the exponent bits are 0, 0, 1 is going to be, these are all filled in with 1s. So this is 1 plus 1/2, 1/4, 1/8, 1/16. That's 1 and 15/16. Okay, times 2 to the negative 2. So this is going to be 31/64. Okay, so we start off, smallest normalized value is 1/4, or 16/64, and we count up 17/64, 18, 19, 20, 21, 22, all the way up to 31/64. Okay, all right. Is that okay? So now, again, imagine the odometer. I add a 1, so it's going to roll over. This is going to become a 1. And then these are all zeros. And what's the next number going to be? the next number will be 32/64 or 1/2. Okay, so if I roll over, now I get 1 here, so my exponent is 0, 1, 0, and then here I have 0, 0, 0, 0. Okay, mantissa bits are all zeros here. Exponent bits 0, 1, 0. Okay, leading digit is this, so this is 32/64, 1/2. Okay, now if I add a 1 here, so, okay, well, let me just back up. My exponent bits are 0, 1, 0, so that represents 2, right? That represents a 2 in binary. My bias is 3, so my exponent is 2 to the negative 1. Okay, 2 to the negative 1. 2 to the negative 1, I've got 1.000 times 2 to the negative 1, so now I have 1 times 2 to the negative 1, or 1/2. That's 32/64. Okay, so if I change this bit to a 1 here, so I'm counting up again, what is that number going to represent? Okay, so we might feel like, okay, well, we've been counting up by 64ths, so maybe the next number will be 33/64ths, but it's not. The next number is actually going to be 34/64ths, or 17/32. And it's like, what? Why are we jumping up by 30 seconds? Okay, let's see what happens. Okay, so if this is what I have, if I add 1 to this, the next number my bit will become a 1 here. All right, so let's see what happens. My exponent bits are 0, 1, 0. These are these 3 bits right there are my exponent bits. That represents the number 2, so my exponent is 2 to the negative 1. Okay, and my mantissa bits are 0, 0, 0, 1. 0, 0, 0, 1. So I've got 1.0001. So this is 1 and 1/16. Okay, but my exponent is 2 to the negative 1. My exponent part is 2 to the negative 1. So this is going to become 17/16 times 1/2, and 17/32. Okay, and 17/32 would be equal to 34/64. So I went from 1/2, or this would be 16/32, to 17/32. And then what's the next number going to be? This will be, this becomes 1, 0. So this 1 and 1/8 times 2 to the negative 1. So that will be 18/32. And if we keep going, we will have 18/32, 19/32, 20, 21, 22/32. And we will keep going until these are all filled in with 1s. Okay? And that will be 31/32. Okay, so at this point, I have 1 plus 1/2 plus 1/4, 1/8, 1/16. That's 1 and 15/16 times 2 to the minus 1. That's going to be 31/32. Okay, 31/16 times 1/2, 31/32. Okay, all right. So if I add a 1 here, 1 bit here, what do I get? What's the next number I'm going to get? The next number I get will be 32/32, or just the number 1. Okay, so here my exponent bits are 0, 1, 1. That's 3 in binary. My bias is 3. So my exponent is going to be 0, 2 to the 0. My mantissa bits are all zeros. My leading digit is 1, so that's going to be 1.0000 times 2 to the 0. So that's just 1. Okay, 1, or 32/32. Okay, all right. If I add a 1 here, what is the next number going to be? It's going to be 1 plus 1 plus what? 1 plus 1/16. Okay, 1 plus 1/16. So here, my exponent is 0. My bits are 3 with a bias of 3. My exponent is 0. And then here, my mantissa is 0, 0, 0, 1. So it's 1 plus 1/16 times 2 to the 0. So that's going to be 17/16. And then if we keep going, we'll go from 16/16, 17/16, 18/16, 19/16. Keep going, and we'll eventually reach 31/16. Okay. And then what's the next number going to be? 32 over 16, or 2. And at that point, we can do the calculations, but it will be, our increments will be 1/8. So this will become 2. So here I basically had 1, 1 and a 16th, 1 and 2/16, 1 and 3/16, all the way up to 1 and 15/16. And now I will have 2, 2 plus 1/8, 2 plus 2/8, 2 plus 3/8. This is 2 plus 15/8, okay? 2 plus 15/8, 15, that sounds so weird to say, 2 plus 15/8, but that's going to be 3 and 7/8, or 31/8, okay? Just shy of 2, all right? So at this point, the increment between values is 1/8, okay? All right, what's the next number going to be? The next number is going to be 4, 32 over 8, or 4. But now my increments will be 1/4. So I get 4, 4 1/4, 4 2/4, 4 3/4, 4 15/4, okay? 4 15/4, 15/4 is 3.75, so this is 7.75, just shy of 8, okay? 7.75, 31/4. And then the next number will be 8, okay? And then now our increments will be 1/2. 8, 8 1/2, 8 2/2 are 9, okay? 8 3/2 are 9 1/2, so on and so forth, until we get to 8 15/2, or 31/2. And that will be 15.5, okay? And then if I take one more bit after this, this becomes all 1s in the exponent. All 1s in the exponent, 0s in the mantissa, means I've reached positive infinity, okay? So this miniature floating point system is very limited. It says the largest possible number I can represent is 15.5. After 15.5, any number bigger than that is considered to be infinity, okay? So it's a very limited system, but the same limitations exist in double precision floating point. It's just the upper limit that's not infinity is a much bigger number, okay? But then it just says, hey, any number after this, we're just going to call it infinity, okay? We also see the same phenomenon where in the beginning our step sizes are small, like 1/64th, and then as our numbers get bigger, our step sizes get bigger. It becomes 32nds, 16ths, 8ths, quarters, halves, and so on. So our miniature floating point system, if we wrote out the number line, okay, there would be a total of 2 to the 8, what is that? 256? 256 unique values that I can represent with 2 to the 8, okay? And in the beginning, our step sizes are 64ths, okay? All the way from 0 to basically 1/2, I'm incrementing by 64ths. In denormalized mode, I'm incrementing by 64ths. In my smallest to normalized mode, I'm incrementing by 64ths, okay? Then once I reach 1/2, I increment by 30 seconds, from 1/2 up to 31, 30 seconds or whatever, okay? And then once I reach the number 1, I increment by 16ths, okay? And then once I reach the number 2, my step size becomes 1/8. And after I reach the number 4, my step size becomes 1/4. After 1/4, my step size becomes 1/2, okay? And I can't represent, like if I wanted to represent 9 1/4, I can't do it. I can only represent either a 9 or 9 1/2. I can either represent only 8 or 8 1/2, right? Like if I look at this number is 8, this is 8 1/2. I don't have any spot to represent like 8 1/4. I don't have any more bits. With only 8 bits to represent numbers, I can either represent 8 or the next biggest number, which is 8 1/2. I can't represent like 8.125 or 8 1/4. I can either do 8 or 8.5. So, our number line, the gaps between our numbers get bigger, okay? And then at some point, the largest number I can represent is 15 1/2, and anything bigger than that is going to be considered infinity. So let's talk about double precision floating point, which has the same kind of things, but just more numbers. All right, so let me give you your first view quiz answer. First view quiz answer is C. C as in cat. C as in cat is our first view quiz answer. Okay. The smallest possible non-zero value I can represent, the smallest positive non-zero value I can represent in double precision floating point is 2 to the negative 1074. It feels like a small number, but it's not zero. Basically, I have all zeros in the exponent. So I've got 11 zeros in the exponent. We're in denormalized mode, so my bias, normally my bias is 1023. Here my bias is going to be 1022. I've got 51 bits, or 52 bits, and 51 zeros followed by 1. So that's basically going to be 2 to the negative 52. So I've just got 0.0000 and then a 1 all the way at the end. So that's going to be times 2 to the negative 1022. So that's 2 to the negative 1074. And I can represent that on the computer. If you type in 2 to the negative 1074, it will say that's 4.9 times 10 to the minus 324. Okay? And if we try to ask for anything smaller, if I say 2 to the negative 1075, R comes back and says, that's 0. Okay? That's 0, right? It's obviously not. In real numbers, this is not 0. It's just a small number. But if you ask the computer, and this is any computer, not just R, but any computer, because this is implemented at hardware level. If you're using double precision floating point, if you ask for this, it's going to come back and say 0. The smallest normalized value, all right, means my exponent is going to, my exponent bits will be all zeros and a 1. So I have a 1. My bias is 1023. So my exponent will be negative 1022. Okay, so that's going to be 2 to the negative 1022. My mantissa will just be all zeros. So I've got 1 times 1.0, 1 times 2 to the negative 1022. And that is my smallest normalized value. And this is what is known as machine double X min. Okay, so you can ask R for properties of the computer, and you'll get, and it will spit something out. So if you say dot machine $ double X min, it will give you this number 10 to the negative 308, and that is the smallest normalized value. It is not the smallest possible value you can represent. The smallest possible value is this 2 to the negative 1074, but this is the smallest normalized value. That's double X min. Okay. Machine epsilon, okay, the second smallest value is going to be 1 plus 2 to the negative 52 times this, okay, times 2 to the negative 1022. So basically, if I just add 1, so if I have, my mantissa is all zeros and then just a 1 bit at the very end, that's going to be 1.00000 all the way to a 1 here. And that's going to be like, this 1 bit represents 2 to the negative 52. And we're multiplying by my exponent of 2 to the negative 1022. And R will recognize that this number and this number are distinct values. X is 2 to the negative 1022. And then Y is 1 plus 2 to the negative 52 times 2 to the negative 1022. And that gives me this number. And if you look at these last the last digits over here, they are distinct, and R recognizes that they are distinct values. You have to change your options to be like options digits 16 or 17 in order to see this. Otherwise it looks the same, but R understands that these are different. Okay, this number that I can add to 1, the smallest number I can add to 1 that R recognizes, or the computer recognizes as being distinct from 1, is known as machine epsilon. Machine epsilon is the smallest value that you can add to 1 so that the result is a number that is distinct from 1, okay? And that is 2 to the negative 52. That's on the order of 10 to the minus 16. And that's why we say floating point precision has approximately 16 decimal places of precision. And that's because 2 to the negative 52, which is our machine epsilon, we're using 52 bits to represent in our mantissa, okay? Which means kind of the smallest number I can increment in my mantissa is 2 to the negative 52. And 2 to the negative 52 is on the order of 10 to the negative 16. So that's why we say floating point numbers have around 16 decimal places of precision, okay? And so this is known as our machine epsilon, and you can do dot machine, $ double dot eps, and this is going to be 2 to the negative 52. Okay, so on the computer I can say, hey, x is the number 1, and I print out x and I get 1. And then y is going to be 1 plus 2 to the negative 52. And when I do that and I print y, and again I had to change the options to say print out like 17 digits or 16 digits, and the computer will print out 1.0002, and I say, hey, is x and y the same value? And the computer comes back and says, no, they are not the same. They are different. Okay, x and y are not the same. Okay. If I try to add anything smaller than 2 to the negative 52, like if I try to add 2 to the negative 53, the computer can't do this. Here I say a is the number 1, b is the number 1 plus 2 to the negative 53. Okay. Now remember, the computer is able to represent really small numbers. 2 to the negative 53, it can represent 2 to the negative 53 because it can represent 2 to the negative 1074. Okay, it can represent 2 to the negative 1074. It can represent 2 to the negative 1022. Okay, but when you're at the number 1, and if you try to add 2 to the negative 53 to the number 1, R can't tell the difference between 1 and 1 plus 2 to the negative 53. Okay, so here I say A is 1 and B is 1 plus 2 to the negative 53. And if I ask the computer, are A and B equal? The computer comes back and says, yeah, those two things are the same value, because it cannot distinguish between 1 and 1 plus 2 to the negative 53. The smallest thing you can add to 1 is 2 to the negative 52. If you try to add anything smaller than that machine epsilon, okay, it can't do it. All right, let's just take a look at what's going on. This is how we represent the number 1 in double precision floating point. I've got 62 digits here, 62 bits. The number 1 is positive, so 0 for the sign bit. My exponent is going to be 0, 1, 1, 1, 1, 1, 1, 1, okay? The exponent is 1,000. This represents 1,023, and my bias in double precision is 1,023. Okay, so with the bias, this exponent becomes 2 to the 0, so just 1. And then I have all zeros in the mantissa, so that's basically 1. 1.000, all zeros in the mantissa, 1 times 2 to the 0. This is the number 1. Okay. The next number I can represent is I'm going to just change this last bit from a 0 to a 1. Okay, that's the only thing. I changed the last bit to a 1. And what is this? This is going to be, I've got 52 bits here, so this is going to be 1 plus 2 to the negative 52. Okay, and then my exponent is 2 to the 0, so it's 1. Okay, so this is the next smallest number I can represent, 1 plus 2 to the negative 52. And we can see I don't have a way to add 2 to the negative 53. Okay, because I only have 52 bits here. If I want to add 2 to the negative 53, I need another bit in the mantissa. But I'm allocated only 64, and so I can't fit in anything else. So the next smallest value, the next number I can add to this, or the smallest value I can add to 1, is 2 to the negative 52. Okay, so that's going to be 1 plus machine epsilon. All right, does that kind of make sense? All right, let me give you your next view quiz answer, which is the letter A. A as in apple. A as in apple. All right, here is a thought experiment. Okay, imagine we run this infinite loop. I start off with x is 0, and then I say while true, so this just means it's going to run forever. I say x is going to be x plus 1. All right, and I just let this go. So it goes 1, 2, 3, 4, 5, 6, 7, 8, keeps going. let's say you walk away from the computer for like a year, okay? Maybe 10 years. You come back and you say, all right, stop, right? You break out of the loop and you say, all right, what is the value of x? What do you think x is going to be? Do you think it will have reached infinity? Because in floating point, we can get to infinity, right? Or will it reach double x max, which is the largest non-infinity number we can represent? Or what do you think will happen? It turns out it gets stuck, okay? It gets stuck at a very specific number, 2 to the 53, okay? It gets stuck. It doesn't go to infinity. It doesn't go to machine double x max, which is the biggest finite number I can represent. It gets stuck at 2 to the 53, and I want to just kind of demonstrate this, okay? So let me just start off here. All right, so here's the number x, and what I'm going to do is I'm going to add 1 to x, and I'm going to print out x. All right, so here I've added 1. I'm going to add 1, and I count it up from, the last is 90, 91, 92. And then if I try to add 1, it's stuck. It's stuck at 92. I can't add 1. So, and if I say, hey, okay, what is 2 to the 53? 2 to the 53 is this number. Okay. So what has happened? What has happened is we have reached a point. So remember, what does our number line look like? Okay, so in our miniature floating point system, we started off counting at 64ths, and we started up. Then at a certain point, our step size grew to 30 seconds, and then at another point it grew to 16ths, and then at another point it grew to 8ths. Okay, the same kind of thing happens with double precision floating point. There's a point in the beginning, your step size is like 2 to the negative, I don't know, 1074, okay? And then there's a point where the step size is 2 to the negative 52, okay? And then there's a point where the step size is 2 to the negative 51. And then at some point, your step size becomes 1/8, then at 1/4, then 1/2, and then your step size becomes 1. And then it reaches a point where the step size becomes 2, okay? And that's what we reach. We reach a point where our step size has become size 2. So again, here's x, right? And I can't add 1, but if I try, I can add 2. Okay, I can add 2, and now I can keep going because now my step size has grown to size 2. If I try to add 1 here, okay, well it is able to get to that, okay? But now it's stuck again, okay? But again, I can add 2 and it will continue counting up, all right? So we're just at a point in the number line where our step size has grown from 1 to 2, right? And then at a certain point, our step size will become 4, and then our step size will become 8, and so on and so forth. Question? I don't know. Okay, let me try x plus 1 plus 1. Well, it looks like it does. Or hold on. So yeah, I'm not quite sure. All right, okay. All right, so let me print x here. Print x. Oh no. X plus 1 doesn't work. Yeah. So I guess it reads left to right or something. So yeah, but yeah, let me try x plus 0 plus 2. Let's see if that does anything. Yeah, we can do that. Okay, but doing 1 and 1 doesn't like that. Whoops. Ah. Yeah. Okay. That's a good question, though. All right, but yeah, so we've reached a point in our number line where our step size has grown to 2, okay? And so I can add 2, but then it gets stuck. We can keep going, and then so eventually our step size becomes 4, our step size becomes 8, 16, and so on and so forth. We keep going, and then we reach this point. This is the largest possible value, finite value I can represent. That's not infinity. And that's going to be basically all 1s and a 0 in the exponent. So that is 2 to the 1023. And then my mantissa is all 1s, okay? So that's basically 1 plus 1/2, 1/4, 1/3, all the way down to 2 to the negative 52. So I can do add 2 sum of 2 raised to the 0 to the negative 52 power, okay? And then multiply that by 2 to the 1023. And that gives me this number, 1.797 something something times 10 to the 308. This is known as double X max, machine double X max, machine X max. This is the largest finite number I can represent. Okay. At this time, our step size is a ridiculously large, well, I don't know, ridiculously large, just a very large 2 to the 970. Okay, so remember, like there was a point where I can't add 1 anymore, right? Because my step size is 2. All right, there's going to come to a point where I can't add 2 anymore because my step size becomes 4. There's going to come to a point where I can't add 4 because my step size is now 8. This is where our step size is now 2 to the 970. And so if I try to take this number and I say, hey, add 2 to the 969, R says, I don't see any difference. A is this number, X is going to be A plus 2 to the 969. In any other part of the world, we'd say 2 to the 969, that's a huge number. But here, to the computer, the difference between this and this plus 2 to the 969 is nothing. I say, if X is going to be A plus 2 to the 969, is that any different from A? And the computer says A and X are exactly the same value. A and X are equal. And then if I try to add 2 to the 970, though, the computer comes back and says, oh, that's infinity, okay? So this is the largest possible number I can represent. If I try to add anything to it, 2 to the 970, the computer blows up and says, that's infinity, okay? But I can't add anything smaller, 2 to the 969, the computer can't detect that, okay? So we have, we run into these weird issues, right? Where I say like, okay, what is 0.1 plus 0.2? In our brain, we're like, that's 0.3. But if I ask the computer, is 0.3 equal to 0.3, or not 0.3, this is 0.1 plus 0.2, is that equal to 0.3? The computer comes back and says that is false, right? Because we're dealing with these approximations, and the approximation of 0.1 and the approximation of 0.2 is not, when you add them together, is not equal to the approximation for 0.3, okay? And so we can, there's a function called all.equal. All.equal is just asks, are they nearly equal? Are they close to each other? And the default tolerance here is 2 to the negative 26, basically the square root of 2 to the negative 52. Okay, square root of our machine epsilon is the default tolerance. And so it just says, are they approximately equal? And that will say 0.1, 0.2 is approximately equal to 0.3. Yes, that is true. There are profound consequences to this, okay? Because sometimes you legitimately have a calculation like A is 1 and B is 1 plus 2 to the negative 52. And A and B aren't equal to each other, because I don't know if this represents a legitimate calculation. But if you do all equal, the computer will come back and say they are all equal. They are, well, they're approximately equal, right? This is the same kind of thing where, remember that calculator? If you did 10 divided by 3, you got 3.333. And if you do 3.333 times 3, you get back 9.9999. And we have to ask, is 10 and 9.999 the same? And on the calculator, like, we think about it, we go, okay, yeah, 10 divided by 3 times 3 should be back 10. The calculator says it's 9.999, but we can say, yeah, that's close enough to 10, Okay, and that's basically what we're doing. But maybe there might be a legitimate calculation where you say, what's the number? And the number could be 9.999. And is that equal to 10? It's not, okay? It's, so, is 1 equal to this? They're not. They're close to each other, but they're not. But this function, all.equal, will say, yeah, they're close to each other. They're nearly equal, okay? Now, one weird thing about all equal is that it comes back, if they're equal, it will come back as true. But if they're not equal, you get back this text that says mean relative difference is this. So that's annoying. So you can wrap that in is true, and is true will either come back as true or false. Okay. There's an issue known as catastrophic cancellation. Anytime you subtract two numbers that are kind of equal to each other, the difference might have like a large relative error. Okay, a large relative error. So this is, they say, let's say you have a ruler that can only measure to the nearest centimeter. Okay, and so if you have like a piece of wood and its length is 254.5 centimeters, when you use your ruler, you get 255. Okay, and you say, well, 255 and 254.5, that's not that big of a difference, right? What's the relative error? It's only 0.002. It's like less than 1%. Okay, what about 253.4? When you use this ruler, you get 253. And what's the relative difference there? Again, less than 1%. But if you take the difference between them, okay, the true difference is 1.1 centimeters. 254.5 minus 253.4 is 1.1 centimeters. Whereas when you use the approximate numbers of 255 versus 253, the difference is 2. So the true difference of 1.1 versus the estimated difference of 2, you have a relative difference of like 82%. So even though the actual values are only off by less than 1% with the approximate value is only 1% different from the actual value, when you take the difference is like way different from the actual difference, okay? And the same kind of thing happens with the computer. So if I say, let's say A is the number 10 to the 16 or 10 to the 17, and B is the number, okay, and then so we'll call B is, let me say A is 10 to the 17 plus 100, and B is going to be 10 to the 17 plus 200. Okay, here's A, here's B, okay? And now, what's the relative difference between what the actual value should be? This is off by 4, compared to 10 to the 17. It's like 0.00000 whatever off. It's off by only a tiny percentage, right? But if I do A minus B, that difference is going to be 96. The true difference is 100. Okay, the true difference should be 100, but the estimated difference here is 96. So we're off by 4%. Okay, whereas like the relative difference of like how different is 10000000192 to 100000200, you'd say like that's like, like 1 over 10 to the 15 or something, like a really small percentage difference that it's almost negligible and you don't really care about. However, when you take these differences, like the amount of error gets suddenly much bigger, okay? And that's known as catastrophic cancellation. And basically, you want to avoid taking, differences of numbers that are similar to each other. Okay, your last view quiz answer today is the letter D. D as in dog. Letter D is your last view quiz answer. All right, we'll end here. Have a happy Valentine's Day. Enjoy your long weekend, and we will see you on Wednesday.